Hey YouTube, how we doing? Today we're talking some nuclear physics. When we're done, don't be afraid to share your thoughts down in the comment section below. And if you like what you saw, make sure to smash that like button and subscribe. Anyway, we last left off talking about atomic structure, and we looked at increasingly correct models of how, our thought of the atom changed as we got more and more evidence. What we came up with was that we have this very small positively charged nucleus at the center of a much, much larger electron cloud surrounding it. So we have a positive center with a negatively charged cloud around it. And it's pretty remarkable how much larger this atom, the cloud, is compared to the nucleus itself. We said that the hydrogen atom itself has a radius of about 10 to the minus 10 meters. So even a tenth of a nanometer, really small. The nucleus itself gets much, much smaller than that even. The nuclear diameter for something like hydrogen is about 10 to the minus 15 meters. And even when you get to much larger elements like uranium, it's still much smaller than the electron cloud here at 10 to the minus 12 meters. And so what we end up with is the nucleus itself is anywhere from, 100 to 100,000 times smaller than the electron cloud. And we get this sort of almost disturbing idea that matter is mostly empty space. It's like, a person standing at the center of a football stadium. That's sort of the ratio of dimensions to what we expect with the nucleus to the rest of the atom. So yeah, even something like the hard surface of a wooden table or a block of lead, mostly empty space. It's really how those electrons on the outside of the atom are able to interact with other matter that give us sort of the illusion or sensation of hardness. So just some food for thought. We're going to focus our discussion today on the nucleus, which, as we sort of learned from Rutherford's model last time, it is composed of positive protons and neutral neutrons. So let's draw a very simple nucleus here. It's one we're going to be really familiar with by the end of the day, and that is the helium nucleus. We have 2 protons and we have 2 neutrons, which I'm going to draw as these little shaded in guys here. We know that 2 positive charges, when they get next to each other, they want to repel. And so the reason that they're able to stay together in this tiny little packet is that all 4 of these particles here are interacting with what's known as the strong nuclear force. So despite the 2 protons wanting to repel from each other, they interact with an even more powerful force that binds them together with the strong nuclear force. And then the neutrons give even more binding force without adding any extra charge, which allows this bundle to be held together even stronger. All 4 of these particles have a smaller bit to them known as the gluon, which is the force that mediates the strong nuclear force. The strong nuclear force is the strongest of our 4 fundamental forces, which also include the weak nuclear force. It includes the electromagnetic force. It includes gravity, which is the weakest sauce of all of those 4 forces. Strong nuclear force on the other end of the spectrum is gravity. It is the strongest force that we know, and it allows these positive charges to stay close to one another. There's something interesting about the way that nuclei bond is that if we took the mass of this system, so we have the mass of 2 protons plus the mass of 2 neutrons, I'll do Mn there, what we find out is that this does not equal the mass of the helium nucleus. It turns out that this is actually less than its component parts. So what happens is when we get these two protons together with these two neutrons, when they bind each other using the gluons and the strong nuclear force, some of the mass has to be converted into energy to hold them together. And that's what this smaller mass here is. It's less in its component parts because the masses that went in to create this nucleus had to be converted to energy to help hold this together. So we can get what's known as the binding energy by using this idea of mass energy equivalence, E equals mc squared. We essentially have c squared is equal to the mass of the nucleus itself minus the mass of the component particle. So we'll do sum of the components over here. And the difference is the amount of energy that's required to bind these together. So this kind of funny fact is that, a nucleus, when you put it together, it loses weight compared to, the pieces that put it together. It's always less than all the component parts because there needs to be some energy to hold this thing together. So a uranium nucleus is lighter than the, hundreds of particles used to put it together. We can sort of describe the mass, the total mass of the nucleus roughly by what's known as the mass number A. This is roughly equal to Z, which is the number of protons. Z is really the effective nuclear charge. But all the charge in the nucleus comes from the proton, so this is equivalent to the number of protons. And we can add to that N, which is the number of neutrons. So this mass number gives us an idea of how many protons and neutrons compose the full nucleus. And for a given element, depending on the balance between protons and neutrons, you can end up with a different mass number, and that gives us sort of the various isotopes that can exist for any one kind of atom. So as we build a nucleus larger and larger, if I have all these little bits there in the nucleus, this is a very massive nucleus here. It's composed of protons and a bunch of neutrons, blah, blah, blah. That one's going to be proton. Eventually what happens is it gets so kind of unwieldy that not even the neutrons there can hold it all together. And eventually what happens is there's not enough glue to hold it together and it collapses. Too big to be stably held together, and we get collapse or decay of the nucleus. So this leads us to our next topic of nuclear decay. What exactly is happening when a nucleus falls apart? Nuclear decay was, largely in part discovered and studied by our good friend Rutherford of the gold foil experiment we talked about last time. He discovered what are known as alpha and beta decay, and we'll expand upon what those actually mean in just a moment here. And for all his work in discovering, the structure and, the destructure of a nucleus, how it can fall apart, he was awarded the 1908 Nobel Prize in Chemistry, which is a pretty prestigious award if I don't say so myself. As a fun sort of side fact, his grad students, the ones who actually did these experiments that got him the Nobel, their names were Geiger and Marsden. So that's the same Geiger. If you've heard of a Geiger counter to detect radioactive radiation, that's the same dude there. And his other grad student was Marsden. While Rutherford got the Nobel, these two guys who actually did the experiment got radiation poisoning. So really the perks of being a grad student were well known way back then. But these people's collective work really helped us understand the underlying structure that makes up the nucleus. So let's talk about alpha decay, which I've mentioned here. Alpha decay, there we go. is essentially a nucleus gets so big and unwieldy that it starts just clustering apart. And it does so that, so a decaying nucleus will emit a helium nucleus. So the nucleus gets so big and unstable that it just starts clustering and crumbling apart in the form of little packets of 2 protons and 2 neutrons. We can represent a helium nucleus by, the helium symbol, He, a little 4 up top and a 2 down at the bottom. More generally, we'll see this notation. We're going to use a symbol X in general. There's no atomic symbol with just a letter X. There's an Xe, but not an X. And so X just sort of represents a dummy atom that we're going to analyze. We're going to use Z down here to represent the bottom number. Again, this is our number of protons. And up top here we have A, which is our mass number. So we can find the number of neutrons by subtracting Z from A. And for any given atom, helium for example, Z will always be 2. Z is a characteristic of that atom. For example, helium is precisely helium because it has 2 protons. You can have a different number here, helium-3, helium-4, helium-5, based off the number of neutrons, whether it has 1, 2, or 3 neutrons or more. I'm sure there's probably other isotopes of helium, but you could have different A values, but helium is defined by having 2 for Z. So in alpha decays, I have some arbitrary nucleus with a value A and a value Z. It's so big it can't hold itself together anymore, and it splits into that helium nucleus and turns into a completely different element, Y. There is actually a Y element, yttrium, but, them's the break. This is not yttrium. This is, in fact, just a second dummy nucleus. So sorry for the potential confusion there, yttrium fans. What happens is that this new element, we have to conserve both particle number A and charge Z. So what happens is this is going to have Z minus 2. And we have to have A minus 4. So that when we add the right-hand side of this equation, just like balancing an equation in chemistry, the numbers all have to add up. 4 plus A minus 4 gives us the original number of mass particles we started with, and 2 plus Z minus 2 gives us the original charge we started with. So here we have conservation of both charge and mass are required. And that's true for any kind of nuclear decay, as we're going to see. So when we are balancing nuclear equations, just like when we balance equations in chemistry, we have to make sure all the numbers add up on both sides. So our alpha decay has a big nucleus clustering away bit by bit. Alpha decay is most common for the largest kinds of nuclei. So when you start getting into the, 60 plus, atomic numbers, that's when we get alpha decay. They're big enough that they can, safely cluster away large fractions of themselves. So that's alpha decay. Beta decay is a decaying nucleus will emit an electron, or there's actually 2 kinds of beta decay. There's one where it'll emit an electron, and there's one where it'll emit a positron. So what the heck's a positron? Positron is an example of antimatter, which sounds really exciting, and it kind of is, but really antimatter is just regular matter with the opposite charge. So a positron has the exact same mass as an electron, but it's positively charged. So it's a little tiny positive bit. So a beta decay, what happens here is we start with our base. So this is one kind. This is electron emission. We have A, Z. It's our base nucleus we start with. We say it's going to emit an electron. An electron does not have enough mass to really count towards the A number here, but it does have a -1 charge. So in order to balance this equation, our daughter nucleus here, the one that forms in this decay, has the same mass number as it did before. 0 plus A gives us A again, but it has to have an additional charge. So this one actually leaps us up the periodic table by emitting, because it emits an electron, in order to conserve charge, we have to go up one so that this one here cancels out with this -1 here, and we get the charge we started with. Electron emission also emits this really neat thing called an antineutrino. We symbolize that with a Greek letter nu for neutrino, and a little bar over it tells us it's the evil twin, the antineutrino. This is an antineutrino. It's a much smaller particle than the neutron. It's even smaller mass than the electron as far as we know, and it has no charge. We discovered that this antineutrino has to be there because of conservation momentum properties. When we first started studying beta decay, when elements would decay by this process, we were finding that the momentum didn't quite add up. And so they hypothesized there had to be some small particle that we couldn't see to make up that difference. And then years later, we were actually able to verify that it did in fact exist. And that's what happened. So conservation of momentum, important quantity when we learned it the first time. It's even important when talking about, more advanced and fundamental forms of physics. So conservation laws are where it's at. So that's our electron emission. What's really happening here is what we have is one of our neutrons. The mass number stays the same. We're not losing a whole cluster of our nucleus like we were with alpha decay. One of the neutrons is essentially turning into an electron and leaving an extra proton behind in its wake. So here we kind of have a neutron turning into an electron and a proton. So we get an extra proton, and in order to make that happen, the charge has to balance out, an electron has to be created as well. So that's how we conserve charge here. A neutron converts itself into an electron and a proton. The other kind, positron emission, starts out the same. We emit something with the same mass as an electron, so it doesn't have enough mass to really change the mass number of the nucleus, but it is a positively charged particle. So in order to balance out charges here, we're not going to get Z plus 1, we're going to get Z minus 1. So we go down the periodic table in this case. So here, before a neutron turned into an electron and a proton, here we have a proton turning into a neutron and a positron. A positron is an antimatter particle. Here we spit out an antineutrino. Here we already have an antiparticle, and so we just spit out a regular neutrino here. Positron emission, or beta decay in general, is the principle behind generally smaller nuclei. So the most common example is carbon-14. It decays via beta decay. Carbon-14 is the one that archaeologists use to date, pottery or other things they might find. Carbon decay does not tell you the age of dinosaur bones. The half-life, which we'll talk about in a moment, is much too short to get back to millions of years ago, so different isotopes are used to date older things. So carbon-14 is probably the most famous beta decayer that we know of. The last kind of decay here is gamma decay, which is an excited nucleus. So you can excite the nucleus just in the same way that you can excite electrons to higher states. So an excited nucleus goes back down to the ground state and emits a high energy photon. Typically, this is literally going to be a gamma ray, but there are some nuclei that decay using an X-ray photon, and that's included within this scheme here. So we have our base nucleus, AZX. I'm going to do a little star here to represent that it's excited. And then it finally decides to drop back down to its state. It's the same exact nucleus. Photon has no mass, it has no charge, so everything is preserved. We go back down to the same state without a little asterisk there, plus the photon that we emit. So this is just a photon. So the nucleus gets really, really excited. Like if you were at a party and you had way too much sugar, you're excited, you're bouncing off the walls. Eventually you don't feel so good, you throw up, and you emit that photon to get back down to your ground state. And that's a kind of, it's exactly what's happening with a nucleus here. It's getting excited, it needs to get rid of that extra energy somehow, and it throws up a photon to get back down to its base state here. So that's our three mechanisms. We have alpha decay, where we emit helium nuclei. Beta decay emits an electron or a positron. And gamma decay, we emit a photon. We can talk briefly about sort of the strengths of these decays and sort of how harmful that they are. Alpha particle has big mass and large charge. Beta particles have small mass and lower charge. It's one lower, but it's still lower. And then our gamma particles have no mass and no charge. And so it turns out that alpha particles are sort of the easiest to block. They're blocky, so they interact with matter more readily. They have a lot of charge, so they interact by the electrostatic force more readily. And these have weakest penetrating power. Beta particles, they have lower mass, they have lower charge, they're able to sneak into smaller spaces, and they interact weaker with the electrostatic force, so they have more penetrating power. And the gamma particle has no mass, no charge. It doesn't really want to interact with matter all that much to begin with, and so it has the most penetrating power. So there is a fun experiment where some sadistic person has baked 3 cookies, each including a different kind of radioactive decaying element. So we have like alpha chip cookies, we've got a beta doodle, it's a snickerdoodle with beta particles in it, and we have gamma crunch. You were told by this madman that you get to put 1 cookie in your hand, you get to put 1 in your pocket, and you get to eat 1. And you want to do this so that you minimize your exposure to radioactive particles. If these particles can get inside your body, they can the radioactive energy can isolate, ionize, atoms and molecules in your body, creating free radicals, and then bad stuff happens. So you want to minimize that ability. You want to minimize the penetration of those particles into your internal organs. It turns out, the way I wrote this, didn't leave much suspense. You want to do it in this way. You want to place the alpha in your hand, you want to place the beta in your pocket, and you want to put the gamma in your belly. The alpha chip, those are so big, those particles aren't really going to even penetrate your skin. So you wouldn't want to hold it there for long, but that would be the safest place to put the alpha. You can put the beta one in your pocket because now you have both the pocket of your pants and your skin protecting you from those more penetrative particles. You have 2 layers of protection. Typically a beta emitter can be blocked with a piece of paper, and so the thin fabric in your pocket's going to be pretty good. And then the gamma one is safe inside your body because most of those gamma ray photons are going to penetrate through you and not interact with your matter at all. So gamma cookies are the most delicious, though I wouldn't want to eat any one of these to be the most safe. All right, so on that delicious note, I will leave you for today. Have a good one.